Hi everybody, we're in my basement once again. We're going to be doing question 2 from the Newton's Laws Qualitative Problems worksheet. Once again, I call these a triple whammy. Alright, number 2. Two persons of identical mass find themselves on a sled, at rest, in the middle of a frictionless frozen pond. One person jumps off the east end of the sled. A couple seconds later, the other person jumps off the west end of the sled in exactly the same way as the first person jumped. Using all three of Newton's laws, describe the motion of the sled during the first jump, in between jumps, during the second jump, and after the second jump. Also, sketch a velocity time graph for the sled. So this is actually quite a long question here. Before I get into that, I want to try to demonstrate what's going on with people jumping off a sled here. That's why I'm in my basement. That's where I do my stunts. Okay. Supposed to be on a sled in a frictionless surface. I don't have a frictionless surface in the basement, obviously, but I'm gonna try to simulate something. Let's use our imagination here. So I've got a carpet here, and let's just say that that carpet is like it's land. All right. So let's say my basement is all water. I'm in a boat, so not a sled, but a boat on water, and I wanna get on the land here. But right now I'm on a boat, so putting these guys down. These are just metal cylinders that I have lying in my basement for some reason. So I have two of them, and they're going to be rollers. That's going to be my best way to try to simulate frictionless surface or a boat on the water. Alright, so this wooden board is my boat. I'm on the boat. And oh, the land is right there. I think I can just walk and step on the land. Or jump onto the land. So let's see what happens. Oh! Right? So, the point is, that was intentional, by the way. That wasn't an accident. The point is, when I try to jump off the boat one way, the reaction force on the boat is the other way. Okay, so my leg pushes backwards on the boat, causing the boat to move backwards, or in this question's case, the sled to move backwards. Whereas the reaction force would be the sled pushing me forwards. And as you can see, I didn't get very far forwards. There's a little bit of an issue with mass there. Right? I'm a lot more massive than that wooden plank. So the wooden plank's going to accelerate quickly backwards, whereas my body will not accelerate that much forwards. I don't think I made it onto the carpet there. Anyways, that's what's going on with this sled question. Okay, people jumping off the sled. Their act of jumping off the sled is actually going to make the sled go the other way. Alright, I'll get back up to my kitchen where we can type out the answer. Alright, we're back upstairs, and let's take a shot at this here. So, during the first jump, let me just highlight the directions here in the question. So, one person jumps off the east end of the sled. Okay, so that's the first jump. Okay, so if the person jumps off the east end of the sled, that means the person went east. So the reaction force would be that the sled goes west. Okay, so during the jump, the sled will accelerate west. And that's a combination of Newton's third law, so N3, since the person moved east, the reaction force on the sled is west, as well as Newton's first law. So the reaction force unbalances the forces on the sled. The sled just was starting at rest. But now that the forces are unbalanced, it will accelerate that way. Okay, so that's what happens during the first jump. Now what about between jumps? Remember, this is a frictionless surface. So after the first person has jumped, the force is gone, okay? There's no longer that reaction force. And in fact, the net force goes back to zero. There's gravity down, there's normal up. They're going to cancel each other out. The net force is zero now, and when the net force is zero, there's no acceleration. That means it'll go at constant velocity. And it'll be in whatever direction it left off going, which was west. So the explanation due to Newton's laws, that would be the first law again, N1. Now that the forces, I'll say now that the net force is zero newtons again, the sled will move at constant velocity. All right, so that's between jumps. Now the second person is going to jump off the sled. I'll highlight that with a different color. So the other person jumps off the west end of the sled. Okay, so if the person jumps off the west end of the sled, so the person moves west, now the reaction force is going to be towards the east. So the sled will accelerate east. And the explanation, you know what? For the explanation, I'm going to save a little bit of the time, and I'll say it's basically the same as part A. Right up above, I explained Newton's third law and first law applying to the first person. Well, it's the exact same explanation for the second person. It's just in the other direction. All right, so I don't mind you doing that in a problem set as well, just so you don't have to write everything out at the same time. Okay, so the sled's going to accelerate towards the east when the second person jumps off. However, there's one more detail that I'm going to add here. I'll give you a few seconds to think about what that other detail might be. What's different between the first person jump and the second person's jump, other than the direction? And that difference is actually going to be mass. All right. When the second person is jumping, the first person's not in the sled anymore. That person's gone. So the whole sled just got a whole lot lighter. All right. So because there's less mass, the acceleration is going to be higher during this second person's jump. So I'm going to say this acceleration is higher in magnitude than when the first person jumped. And the explanation is Newton's second law, N2. With the first person gone, the sled has less mass, so the acceleration is greater. Okay, Newton's second law, acceleration equals force divided by mass. All right, so after the second jump, what's going on? Well, There's no more forces on the sled. Well, no, there are forces on the sled, gravity and normal, but they're balanced out. So the net force is 0 again. So it's going to go at constant velocity again. And it's going to be in the east direction. Okay, because as we said, the acceleration going east was higher in magnitude than the acceleration that was going west from the first person jumped. So overall, the sled's going to end up going east. And that's Newton's first law again. Forces are balanced. Okay, we already explained it in a bit more detail up here, so I'll do it more simplified down here. Newton's first law, the forces are just balanced. All right, so that is how I'll answer this question here. It is quite a bit here. This is typed out. It looks little, but if you write it out by hand, it's going to take up quite a bit of space on the page, actually. So what I'd like you to do is go to the next section on Google Classroom. It's got a hand-in folder. Okay, it's called a hand-in folder triple whammies. And in that section, I provide you with this file right here, exactly as it is now. And you can open that, and that's your notes. And everybody's going to get their own copy of the file, so you can edit it if you want, add extra notes, and only you can see that. The hand-in folder will have a second file in it, and that second file has a third example, which I'd like you to try to complete yourself. Okay, and when you're done that, you can click on Turn In, then I'll get your file, and I can make comments on it and return that feedback back to you. Okay, and after I return it to you, if you want to make corrections and resubmit it, you can do that as well. This is not worth marks. This is just something you want to do to make sure you're getting it right, because there is a problem set at the end of the week where you'll have to do one of these as well. So this is your chance to get feedback before you hand in the one that counts for marks. All right, thanks for watching. I will see you next lesson.